Hey guys, and welcome back to a new Android tutorial in which I will show you how you can use DataStore Preferences, so that a modern solution in order to store preferences locally in your Android app. And not only how you can use DataStore, but also encrypt what you are saving, because it's quite common that we actually need to encrypt local preferences. Like, for example, if you authenticate a user, the backend returns some kind of auth token. And then that should definitely be encrypted, because anyone who gets access to that token would be able to make requests in the name of that logged in user. And there was an official library for this, which was encrypted shared preferences, which I don't know if it's actually officially deprecated, but at least the support is discontinued, which is quite sad because now we don't have any official solution for encrypted preferences. But that is why I want to make this video. And yes, maybe some of you know that already, that I do already have a video about encrypting DataStore. But over time, people reported a few issues with that approach in the GitHub repository. So I really wanted to make an updated video on that, which will replace the older video. The main idea will be the same, but we'll do some tweaks to that previous video that will now work more stable. If you don't know that previous video, then really just treat this as a video that teaches you how to encrypt DataStore. And all you need to do in order to follow through this video is just add the same dependencies that I already added. So you can see this is my version catalog here in a blank new Android Studio project where we have DataStore Preferences. So the version for that at this point 1.1.1 and Kotlin X serialization JSON, since that is how we will save our preferences locally. We then have the same here. So you can, of course, find this code here in GitHub down below. We'll just copy paste this, as well as the Kotlin serialization Gradle plugin, which I've then also applied here. Gradle plugin. And if we scroll down, those two dependencies for DataStore Preferences, as well as Kotlin serialization JSON. If you've done that, we can get started with coding. Now let's open our project structure and we take a look. Here in our root package, I first of all want to create a crypto class, which will be kind of the heart of our encryption and decryption mechanism, which just implements all that crypto logic. This can be an object, since it really just exposes utility functions. And before we get started with writing actual logic to encrypt and decrypt, let's declare some constants that we need here. So on the one hand, we need a key alias. So every encryption and decryption here works with a so-called key. And that key needs an alias, so we can just use that alias in order to then retrieve the actual key, which we will store in Android's KeyStore. So just as a very basic introduction to how encryption works, we have that key, which is really like your key at home, that allows us on the one hand to encrypt a certain set of data. So in our case, that will just be a byte array, which could be anything. And at the same time, we can use the key to decrypt that encrypted mess from before again. And now it's of course important that this key can't easily get into the hands of an attacker, because everyone who has that key can also decrypt our data. And that is why Android offers us this Android KeyStore, which, as the name says, is the official solution or the official recommended way to store such encryption and decryption keys. And in order to just uniquely identify our key, we need to give this an alias, for example, just secret. We're just dealing here with a single key, but depending on your application, you might work with multiple keys, and therefore we need an alias in order to identify one of these. We then need a private const val for our algorithm, so the cryptographic algorithm that we want to make use of here, and that is equal to key properties from Android Security KeyStore dot key algorithm AES. That is a symmetric encryption algorithm that is quite popular. Then we do want to create a so-called block mode, which as well just specifies a bit how the encryption works. So how the blocks are actually, how the encryption is separated into blocks. The typical algorithm here is CBC. So we can set this to key properties block mode CBC. We then need a private const val to declare some padding that is being used for the encryption, which you can also get with key properties. Here we want to use encryption padding PKCS7. And then one last constant that just bundles the algorithm, block mode, and padding. That is just the format that the encryption classes here expect this in. So we call this a transformation, which is in the end just our algorithm together with the block mode and together with the padding. So just with a / between these. And with this transformation, which now bundles our chosen cryptographic config, we can create a private val for our actual cryptographic cipher. And we can get this with cipher from JavaX crypto dot get instance. And here we need to now pass in this transformation that we've created before, which needs to be in this format. So the cipher now contains information about how we want to encrypt something. What we now also need is our KeyStore reference, so the actual place where we want to store the cryptographic key. So KeyStore is equal to KeyStore from Java, java.security. We want to call get instance, and on Android specifically, this instance is called Android KeyStore. Let's move this in a new line, and then we can also say that apply, and we want to load this KeyStore, so we actually get the reference in our we get a real reference we can work with. This can require certain parameters if you want to further configure this, or you can also simply pass null here, since in our case we don't need to configure this in any way. All right, now what we need to do is we need a way to actually generate a key that we can then use for our encryption and decryption. This can happen in a new function, private function create key, and this will return a so-called secret key. And here you can then return key generator dot get instance again. We need to pass in the algorithm we want to use, so we can simply pass in our algorithm from above. We can then call that generate key in order to generate that, but in between we want to apply certain config. So we can say apply, and we want to initialize this key that takes in this algorithm parameter spec. And here we can pass in a key gen parameter spec dot builder, and we can use this builder to configure how we want to generate this key specifically. So on the one hand, we want to pass in our key alias for the KeyStore alias, and the purposes, so what we want to use this key for, is on the one hand, key properties dot purpose encrypt, or key properties dot purpose decrypt. That is what we want to use our key for both these purposes, of course. And then we can just call all those set functions in order to configure how this key will be generated. For example, setting the block mode of that key to our block mode from above. We can then set the encryption paddings to our padding that we've specified above. We can set randomized encryption required to true. Randomized encryption pretty much just means that our goal is that if we are encrypting the same byte array, the same data twice, that we get different outcomes, that we get different encrypted byte arrays out of that. So for example, you want to encrypt the string hello, then every single time you encrypt that string hello should lead to different encrypted results. That is of course good for security, because otherwise if an attacker notices that certain values in their encrypted form are being the same, then they can make the assumption that the decrypted string also must be the same. And that's of course not what we want. We want to randomize this a little bit so that we pretty much just use a so-called initialization vector, so an IV, which is in the end just a random sequence of characters, of numbers, of just a random sequence of bytes that we prepend to our actual data that we want to encrypt. And since we just always add another randomized sequence of bytes, the entire outcome of our encrypted byte array will always be a different one. And with this option, we just set this to required, that we say, hey, we want this extra level of security. And then a last option we want to apply is set, set user authentication required. I want to set this to false. So this you could set to true if you only want the key to be usable if the user is authenticated, so via a biometric prompt, for example. If you need this extra level of authentication, for example, if you're working on a banking app, that would make sense that the key can only be used when the user is actually logged in and sees their bank account to then maybe load some encrypted bank account data. I don't know. If you need this extra level of user authentication of security, then set this to true. In our case, we don't have any authentication layer in our app, so we can just leave this at false and then call build. So this function is now used to generate a new key, which will be called the first time we actually want to save something. But once we already saved something, then that means there is already a key that we can retrieve for the subsequent uses. So we also want a function to get an existing key, and this will return a secret key. So we can check if there is an existing key, which is equal to our KeyStore, since that is where we store our key, and we call get key, which returns a nullable key. The alias is our key alias, and I actually wanted to call get entry, this one here, not get key, because here we can also pass in these protection parameters, which we don't need. We can set this to null, and then cast this as a nullable KeyStore dot secret key entry. So what we do here is we check if there is an existing key that is already saved in KeyStore. If there is one, this will be non-null. But if there is no key yet, so for the first use, this will be null. So we can just return our existing key. But if that is null, we simply create a new key. And what is it complaining here? Requires secret key, found secret key entry. We need to check for existing key, that's secret key. All right, and that's really all the utility that we need inside of this class in order to now start encrypting and decrypting. Since we now have a key that we can use for this encryption and decryption, we have a place to store this key safely. We have a cipher that we've configured here with our encryption and decryption configuration, and we have logic to also create a new key. So now down here, the only two public functions we want to have is a function to encrypt something, specifically a set of bytes. That will be a byte array. And here we can now call cipher.init, so I want to initialize our cipher, and the op mode that we need to pass here is pretty much just what we want to do. In our case, we want to encrypt, so we can set this to cipher.encrypt mode. And the key that we want to use for encryption will be whatever our getKey function returns. And getKey, just recap, returns our existing key if there is one, and otherwise creates a new key. We can then create our IV, so our initialization vector, which as of that is really just a sequence of random bytes. That is luckily already done by this cipher. So you can see we can set this to cipher.iv, and then we can encrypt our actual data. And that can be equal to, let's call it encrypted, that can be equal to our cipher, and we call doFinal, which will really encrypt whatever we pass in here, and those that will be our byte array. What we can then return here, since this encrypt function should of course also return at the finally encrypted byte array, we can then return our IV byte array plus our encrypted byte array with the actual encrypted data. And since we always have a unique random initialization vector, we always return a unique sequence of bytes, even if this byte array here is the same across encryption attempts. And in our decrypt function here, we really just want to reverse that. So here we get in our byte array again, the encrypted one in this case, and we want to return the decrypted byte array in this function. And we can then say, we first of all retrieve our initialization vector, since we of course need to consider that in our encrypted byte array now. And we can get this with bytes.copy of range. So we want to create a copy of a certain range of that byte array. We can say from index to index. From index is simply 0, since the initialization vector starts here at index 0. And it goes to our cipher.block size. So just one block. However large one block is in our cipher, that will be our initialization vector. And then we can get the actual data, which is also bytes, copy of range. And now we want to start with our cipher.block size and go to bytes.size, so to the very last index of that bytes array. And then we can just use our cipher to again initialize that, this time with the decrypt mode. So cipher decrypt mode. And the key in this case is again getKey, which will at this point return the key that we've already stored in our KeyStore. And then we can return cipher.doFinal again, which in this case will decrypt, since that's the mode that we've assigned here. And we want to pass in our actual data byte array. And we're not yet using the initialization vector that comes inside of our init function here as a third parameter, but we can pass in this IV parameter spec in order to pass in this IV here. So that will also be considered for decryption. And that was already the hardest part of this video. We of course still have to get to the part where we want to now use this utility class for data store. So we can also really easily store encrypted data. But that's really not too difficult anymore. In the end, what we now want to do is want to create a so-called serializer for data store. So just a class that defines how data is being saved when we save it with a data store. And first of all, let's think about what kind of data we actually want to save here and encrypt. In our simple example, let's just store simple token reference or so. So we can say something like a user preferences or so. Make this a data class. And in here we store our token. So anything we put in here in this user preferences class will then be saved encrypted. And we want to make this a serializable, so we can serialize this with Kotlin X serialization. And then below here, we can then create our serializer. This can be an object called user preferences serializer, which is a serializer from Android X DataStore.core, and we pass in our user preferences object here to make sure the serializer is used for user preferences objects. We can then hit Command I to override these three functions and values. On the one hand, the default value should be pretty clear. Here we can just initialize our user preferences object. Let's give this token a default value of null, and then we will just use the default values here of this class as the default value in DataStore. If we call read from, then that means we get an input stream, and we need to now read in that data from DataStore that we've already saved and return that as a user preferences object again, since that is what we want to save with DataStore. So what do we need to do in here? Let's actually start with a write to function, because here we would already have to deal with encrypted data. Let's do it step by step, and first of all, care about encrypting our data, and then decrypting that in read from. So now write to function, we on the one hand get a user preferences object, and we now need to write this to our output stream in order to save it in DataStore. So the first step is we need to somehow convert this user preferences object to an object that we can easily save in DataStore. So for example, a JSON object. So we can say we have a val JSON, where we say JSON, so this comes from Kotlin externalization, and we encode something to a JSON string, specifically our T, so our user preferences object. Now the next part is that we actually want to take this JSON and convert it to a byte array. So our actual bytes that we now want to save is simply JSON.toByte array. These are now the raw unencrypted bytes, which we now want to encrypt. So the encrypted bytes is equal to crypto.encrypt, and we pass in our bytes. And something that was necessary here in order to avoid certain crashes is that we now take these bytes and save these as a base 64 encoded string in DataStore. So we can say val encrypted bytes base 64 is equal to base 64. Here from Java util dot get encoder, and we want to encode a byte array to a string. That is what we want to use, and the byte array is simply our encrypted bytes. It is complaining here, okay, API level, we can simply bump this up. I don't even want to support 24. Let's bump this to 26 here in our Gradle file, then go back to user preferences, the error will be gone, and then we can make use of that. Because now we can say with context, so we call this on the IO dispatcher for IO optimized operations, and we say we take our output stream and we use it, so it's also being closed automatically, and we say it.write our encrypted bytes base 64, and we convert this back to a byte array. And that is how we save something encrypted in DataStore. So now in read from, we need to take this and just reverse this process in order to decrypt what we've saved before. So we do have our encrypted bytes on the one hand, encrypted bytes, that's equal to what we get from our input stream. Here we can also use with context, which probably is already used by DataStore under the hood, since these are suspend functions. But here we can then use input.use, and we call it.read bytes. So we read the entire content of our input stream, which is now the encrypted bytes, since that is what we've saved. And then we can take these encrypted bytes and convert these to decrypted bytes. That is what we want to do. So we call crypto decrypt with our encrypted bytes. But here at this point, we also again need to decode this again from base 64. So let's say encrypted bytes decoded, for example, is base 64 again, get decoder in this case. And we want to decode a byte array, which is our encrypted bytes, and then we can pass the encrypted bytes decoded here. And I wonder if there's actually also an encode function that takes a byte and returns a byte array. Yes, this one here, because then we don't need to convert it back and forth from and to byte arrays. Let's do it like this. Okay, so now we have our decrypted bytes. We still can't work with the byte array yet, so we need to convert this back to a JSON string. And then we need to take this JSON string and convert it back to a real Kotlin object. So we have our JSON, well, let's call it decoded JSON string. That is equal to our decrypted bytes that decode to string. And then as a result of that, we can return our user preferences object. So our decoded JSON string, or actually, let's use JSON here, JSON.decode from string, and we pass in our decoded JSON string. that is how this should work. So we now have a serializer, which we can make use to serialize and deserialize data in DataStore, encrypted. So all that's remaining now is I'm going to go to main activity and just add a simple setup so we can test this whole thing. First of all, in order to get a reference to DataStore that works like this, we have a field here where we extend context and call this DataStore, and then use the delegate to say by DataStore, give this whole thing a file name, so the name of the file where we will save our encrypted data. This can be user preferences, for example, and the serializer that should be used for that data should be our user preferences serializer, just like that. And then here in main activity, in our compose content, let's just have something, let's just have a simple row with 2 buttons or so, something super simple. So one button that is used to encrypt something. So text is encrypt. We could have some kind of string here that we actually want to encrypt. So of course this could be dynamic in an app, but we can just say we have a private const val secret token that we want to save. And let's say this is some kind of random sequence. I don't know, let's say we have 1,000 characters and we map these to, I don't know, some kind of range here. We say we have A to Z plus capital A to capital Z, and maybe also numbers plus 0 to 9, like this. And then we take all that that resulting range and we call random, like this. So we just say we generate a random string with 1,000 characters, and then it can't be a const val, but can just be a normal val, which right now is a list of characters, but we can say join to string in order to use no separator at all. So we will really just create a string out of all that, out of all those characters that we've generated here. Then we have a secret token, which is generated at runtime. And then here in our button, we can say we make use of our data store, that update data. That is what we want to do. That is also a spanning function. So we need to coroutine scope. We can say about scope is remember coroutine scope. In a normal project, I would of course do things like this in a view model or some kind of data layer. But to keep things simple here in this video, which is all about this encryption thing, let's do it in the UI directly. So we launch the scope directly here, scope.launch, include our update data in there, and here we now get a reference to our current user preferences, but we can also just say we want to update our preferences with a new user preferences object and set the token to our secret token. On the other hand, we also need another button where we can load the encrypted data. So we also need some sort of state where we load the actual decrypted token, text by remember, mutable state off, and that's just an empty string by default. And then if we click our button, our decrypt button, this now is decrypt. If we click this button, we don't want to update our data, but rather read data. And then we can say our text is now datastore.data, which is a flow of user preferences. So you could of course also take this flow and automatically listen to changes. Then you would have a really reactive UI, which would make sense. But I really want to show you that first there's no data, and when we click our button, then we load it. So we say text is datastore data.first, and then refer to the token. We have a nullable string here. Okay, if it's null, we just use an empty string again. And then we just need something to also display that text. Let's just make this row a column. So it'll be a super ugly UI, but it will do its job in order to show you this. We can apply this inner padding here with modifier padding, inner padding, and then below these buttons, we just display a text composable that shows our text that we've loaded from our encrypted preferences. Okay, let's try this out. I am actually curious and excited whether I missed something or not. But now, when we actually click encrypt in our app, we should be able to really save this randomly generated secret token in our local preferences. So Grail is building, and when we then actually click decrypt, we should again decrypt that message again from our preferences. And from this point on, we should also be able to freely extend this user preferences object here. So whatever fields you add here, I don't know, first name, last name, email address of a user you want to save locally, that will automatically then be encrypted when you save it in DataStore with this serializer. So here we have the encrypt button. Let's click this. and that looks good because nothing crashed. We can also confirm that something was really saved by opening our, I think it's device manager? No. Let's go to these triple dots here and open the device explorer. That's how it's called. So we can pretty much just see the file system of our app. Go to data, and here I want to search for our app name. So encrypted data store. There we go. Open this. Open the files. Here we have a data store folder in which we do see our user preferences file. If we open this, then this is pretty much what was saved. And we can already see that this can't be our plain text token since we did not generate slashes with that and also not special characters like a plus. But this is pretty much our encrypted data now. But we can also confirm this because if we now relaunch the app to make sure it's really saved, if we now decrypt that, we should see a text that represents our token, which is definitely different than what we see here. So we click decrypt, and there is our token. You can see that is definitely a different token than what we had before. But we can also really replace the secret token with something like hello world or so. If we then relaunch this, then we will just encrypt the hello world string as a secret token. If we encrypt this, then this will be overridden in our preferences. We can, of course, again, open the device explorer, reload that file. You can see now it's something different. And if we then click decrypt, we do see our hello world string again. Very, very cool. And technically, DataStore also works for Kotlin multi-platform projects. So if you're curious if this also works for these kinds of projects, yes, but it does require quite some adjustment. So DataStore is actually the same. So the serializer here will stay the same, but how encryption works, that is completely platform dependent. So this crypto class here heavily relies on Java APIs, on Android APIs. So we can only make use of that for Android or for the Android side of a Kotlin multi-platform project. But on iOS, encryption works different. There's probably a different or an equivalent to the Android KeyStore, but for iOS, then we have desktop platforms where you have different operating systems, like Windows will probably handle encryption differently than Linux, than macOS, and so on. Maybe there is some kind of a platform-independent API for encryption. I don't know. But this is definitely how it works on Android. The idea will be the same for other platforms. But if you want to make this work for KMP, then you will need some adjustments. Awesome. Down below in this video description, you will find more advanced Android premium courses, which you can really follow if you say you want to make 2025 your year as an Android developer to really get ready for the industry. I know there are so many different topics in Android development that are confusing people. They don't know where to start. They don't know how to properly learn these. And these courses are really structured intentionally to prepare you from A to Z to be fully ready for the industry and take on a real job. So check these out. Thanks so much for watching. I will see you back in the next video. Have an amazing rest of your week. Bye-bye.